Hello everyone, Mr. Fawcett here, and we are back with another lesson about derivatives. Today we're going to look at some special derivatives, specifically the derivatives of four functions: sine of x, cosine of x, e to the x, or the natural exponential function, and the natural log function, or ln of x. Now, we're not going to go through any formal proofs in this video. I will make another video that shows you the proof for sine of x and cosine of x. We're not going to include it in this video because it's not absolutely necessary to know, especially as both as we move forward with the course as well as for the AP exam. So you'll need to know what the derivatives are. You will never be asked to prove them on an exam. Now, I'm still going to make a video about it because I think it's interesting and I think it's always good to understand the why behind whatever we're learning. So I encourage you to check that out. We're just not going to keep it as part of this lesson video because the proofs are a little intense. So we're just going to put out a separate video for those. What we are going to do is go over what these derivatives are. We're going to talk about three other derivative properties, and then we are going to focus on some practice problems. So we should be able to get through this lesson all in one video. If not, we'll break it into two, but we should be able to get through it in one. So let's jump in and get started. Let's go down to the third page. All right, so the derivatives of sine and cosine. Now get ready, this is super complicated. The derivative with respect to x of sine of x is, drum roll please, cosine of x. I was just kidding, it's not super complicated. So the derivative of sine of x is cosine of x. Now, this may make you think that, that the derivative of cosine of x would be sine of x. However, if you watch the proof video, you'll understand that this is not fully correct. The derivative of cosine of x is negative sine of x. So don't forget that negative sign. And you're going to be using these so often throughout the rest of the course that you're eventually just going to know them like the back of your hand, regardless of whether you understand the proof behind them or not. Now, the derivative of the natural exponential function, so e to the x, is, this one's nice, it is equal to itself. So pause the video, take a minute to think about what that means. See if you think about if you could explain that to someone in words. What does it mean if the derivative of a function is equal to the function itself? Okay, so essentially what this means is that the slope of the tangent line at any point on this function is equal to the value of the function. This exponential function e to the x has some special properties that allows that to be true. The derivative of the natural log function is different. It is not itself. It is actually equal to 1 over x. Okay, so these are the four you need to know. You're going to be using these so often, I'm not worried about you not being able to memorize them. But the quicker you memorize them and you're able to work with them more efficiently, the better, as we move forward with newer and newer things. Okay, in addition to these derivatives, we're going to look at three derivative rules or properties. One of them is the constant multiple rule. So these properties are all similar to the properties we talked about for limits. They will look the same, we just have a different operator. Instead of taking the limit, we are now taking the derivative. So for the constant multiple rule, if f is a differentiable function and c is a real number, then c times f is also differentiable, and put this into symbols, the derivative with respect to x of c times f of x is equal to c times the derivative of f, or c times f prime of x. Okay, two things I'd like to touch on here. The first is just, again, I want to quickly talk about this derivative operator. I know we have before in other videos, but it doesn't help to get a refresher. This is just telling us, one, to take the derivative, and two, to take the derivative with respect to x. So we're taking the derivative with respect to x, namely because this is a function of x. Okay, if we wanted to take the derivative of a function, and let's say we had a function f of, oh, we can throw in any variable we want. We'll say f of theta, because we'll see that later. Well, then we would say take the derivative with respect to theta. Not equals, but brackets. Okay, and it's not a hard rule that whatever the variable in your function is, that's the variable you have to take the derivative of, because there may be some other things about the problem, especially word problems where you're doing something else. But for right now, this derivative operator, the denominator is telling you what to take the derivative with respect to. And generally, these two things are going to match. Not in every case, but as a general rule, that's true. Okay, the second thing is I want to quickly give you an example of what this rule is. Let's say we have a function f of x equals x squared. So a simple function that we already know how to take the derivative of. If we did that, f prime of x is equal to 2x, right? Just using the standard power rule. Now let's say I threw a constant in front of our f of x. So let's say I had 4 times f of x, right? And let's say I wanted to take the derivative of this. So the derivative with respect to x of 4 times f of x. Well, for this function, there's two ways we could do it, right? We could just say this is equal to the derivative with respect to x of 4x squared, and this would be equal to 8x, again using the power rule. But sometimes, especially when you don't have polynomial functions, or maybe you have trig functions or exponential functions, you can't just combine the constant with the original function and do something simple like the power rule. Sometimes you've got to separate the constant from the function before you take the derivative and then put it back there at the end. So what I mean is that another way of doing this is we could essentially factor out the 4 from the derivative expression. So we could say 4 times the derivative with respect to x of f of x. Well, oh yeah, we can leave it like that. I'll just do another line. Of f of x is equal to 4 times the derivative with respect to x of x squared equals 4 times 2x, which is equal to 8x. So we end up getting the same derivative at the bottom as when we just combined the constant with the function and then used the power rule. It was just a different way of doing it. So you can incorporate the constant right away, or you can factor it out and then put it back in at the end. Both ways are going to get you the same result. Okay, the sum rule. This one's pretty straightforward. The sum of two differentiable functions f and g is itself differentiable. Moreover, the derivative f plus g is the sum of their derivatives f and g. So let's put this into symbols. The derivative of a sum of two or more functions, I'm just going to say two functions for now, is just equal to the derivatives of the sum of the derivatives of the individual functions. So that's equal to f prime of x plus g prime of x. So you can just take the derivatives of each individual function, then add them together at the end. You could combine the functions right away, right? But as we saw with limits, sometimes that's not very feasible, right? Sometimes it's much easier to take the limit, or in this case, the derivative of each individual functions, than add the derivatives together. And finally, the difference rule. Let's just use black. So the derivative with respect to x of the difference of f of x and g of x, same idea applies, is equal to the difference of their individual derivatives. Okay, so pretty straightforward. Work the same way with limits. And now let's move on to some problems and see if we can get through I believe we have 4 to do. 1, 2, 3, 4. Oh, 6 to do actually. We'll see if we get through all of them. We may just get through 3 to 4. It says find the derivatives of the functions. Evaluate the derivatives when necessary. So sometimes we'll just be asked for the general derivative. Sometimes we may be asked for the derivative at a specific x value or theta value, etc. Number 1, f prime of theta is equal to something. Now, let's look at this first term right here. That pi over 2 is a constant, so that's just going to stay, right? Then we're going to multiply that by the derivative of sine of theta. Derivative of sine of theta, we know from up above, is cosine of theta. Then we're going to subtract the derivative of cosine of theta. Derivative of cosine of theta is negative sine of theta. Let's simplify. F prime of theta is equal to pi over 2 cosine of theta plus sine of theta. So just make sure you keep your signs right here. Don't forget a negative, etc. Notice that we also used the property of derivatives talking about the difference of two functions. So we first took the derivative of this piece, and then we subtracted it by the derivative of this piece. Okay, because we can't combine the sine minus the cosine of theta. We need to take the derivatives of those individually and then combine. Okay, number 2, f prime of x. Well, first we have a polynomial function. We have x squared, so that's a pretty easy derivative. That just gives us 2x. Then we subtract that by the derivative of this function. Well, our constant stays, and the derivative of sine of x is cosine of x. And there is nothing to simplify, so a nice one-liner. Okay, again, hopefully you've stopped the video and you've tried to do these on your own. We are going to go through, well, we'll see if we can get through all of them. Let's move on to number 3. It may become a little tougher as we go. Number 3 gives us an exponential function as well as a trig function. Let's use pink. So I get f prime of x. Now again, our constant just stays. Our constant does not change. And the derivative of e to the x, right, we already have our 3/4. E to the x stays the same for its derivative. Okay, right, the derivative of e to the x is e to the x. Plus 3, and then the derivative of cosine of x, which is negative sine of x. So if we just make this look a little nicer, we get 3/4 e to the x minus 3 sine of x. Now again, the better you get with these, you'll just be able to rewrite this as negative 3 sine of x eventually right away. I'm just showing you each step individually because we're kind of new to all this for the most part. Number 4, another f of x function, but this time we're asked to evaluate it at a certain x value. So at the end, we'll actually have to substitute in pi over 4 for x and get hopefully an actual real number. So f prime of x is equal to 2x plus 3, and then the derivative of sine of x is cosine of x. So that's our derivative. Now we need to find the derivative at x equals pi over 4. So f prime of pi over 4 is equal to 2 times pi over 4 plus 3 times cosine pi over 4. You're going to need to think back to your unit circle. This is going to give me pi over 2 plus 3. Cosine of pi over 4 is root 2 over 2. So this gives me pi over 2 plus 3 root 2 over 2. And again, if this was a calculator portion of the AP exam, we would round this to, or round or truncate to 3 decimal places. Here, if it doesn't say to round, you should give the exact value. And this right here is the exact value. If you rounded or truncated, it would no longer be an exact value. And exact value is best unless they say to round. All right, let's see what the last 2 problems look like. Based on their length, we will stop it or cut it short here. Let's actually do one more so we can take a derivative using the natural log. Let's do number 5. We also have a radical here, which is good. So whenever you see a radical, before we use the power rule, it's always easier to rewrite. So I'm not going to start with my derivative. I'm just going to rewrite my function f of x. So this is going to be x to the power of 1/2 plus the natural log of x. Now if I take the derivative, power rule should jump out at you. Multiply the exponent by the coefficient, so 1/2 x, and then subtract 1 from the exponent, so x to the negative 1/2 power. Derivative of natural log, we saw from up above, is just 1 over x. All right, I am going to rewrite this. I'll first rewrite it using exponents, and then we'll go back to radicals. I'll make it easier. So I get 1 over 2x to the power of 1/2 plus 1 over x, which is going to give me f prime of x equals 1 over 2 times the square root of x plus 1 over x. Now, if you're comfortable evaluating when you have exponents rather than radicals, well, then just keep this line and evaluate there. If you're more comfortable with radicals, then keep this line and go from there. I need to evaluate at x equals 4. So at x equals 4, f prime of x is equal to 1 over 2 times the square root of 4 plus 1 over 4 gives me 1 over 2 times 2, which is 4, plus 1 over 4 gives me 2/4 or 1/2. And that is the slope of the tangent line of this function at x equals 4. All right, so of course, try number 6 on your own. But we're going to cut the video off here. We're about at 18 minutes. I look forward to seeing you next time. Until then, as always, this has been Mr. Fawcett. Enjoy the rest of your day.